let's begin. Okay, so today's class is about logarithmic time prediction. And there's several different scenarios where you might want to think about this. One of these is a simple search scenario. So back when I was teaching the NYU large-scale machine learning class, there was you could type into a search engine and you could say NYU large-scale learning, and it would actually return, one of 10 billion web pages, which was relevant. So that's kind of an instance where you want to choose amongst a very large set. That set is not really structured in advance in any particular way. Another scenario would be sort of the who is that scenario. So there's a lot of photos getting uploaded to Facebook these days. You'd like to know who's actually in each photo, or at least certain organizations would like to know that. This is actually my brother and his family and their neighbor. Okay. So there's that, well over 10 to the 9, approaching 10 to the 10 billion, 10 to the 10 people on Earth. So there's a lot of possibilities for who could be in any individual photo. So when you get up to these kinds of scales, you tend to see a lot of relatively ad hoc systems for trying to solve these problems. And so today's class is really about how to create a learning system which can approach these scales and do it in an efficient manner. Okay, so the problem today is very simple. It's just multi-class prediction. So you see features, you predict some label, and then you learn the truth. And that repeats over and over again. And now the only twist is that you want to do it, you want to minimize the error rate, and you want to do it fast. So I'm looking for something which is logarithmic time, both at testing and training. I think it's actually important to have it in both cases. There's some people who've worried about logarithmic tests, but linear train. I think that doesn't really work when you get up to 10 billion or whatever. Okay, so first thing to understand is there's a lot of tricks people use to avoid actually directly doing logarithmic time prediction. So the number one trick is you just kind of hope that the number of classes is small, and that's true in practice for most classification problems. The number two trick is to take advantage of a hierarchy to learn to make k small. So you learn a different classifier for every individual node in a hierarchy, and then you put them together to get a large k multi-class classifier. Okay, so then another very common trick is you have a shared representation, and this can be very powerful. This is actually statistically good because you can reuse parameters across many more samples than you could if you didn't have a shared representation. So when people do ImageNet, they typically have a big shared representation, and then they have some sort of fully connected output layer where they predict 1 to 1,000 classes or something like that. Okay, so I mean this is effective for the shared part, but if the output layer has 10 to the 10 elements, it's not going to work very well, right? The amount of state required is just going to be enormous, and the computational requirements are going to be atrocious.
This is happening in machine translation.
Machine translation goes up to about 100,000 classes.
And the softmax.
Yeah,
that's expensive.
It is expensive. Yeah, you would prefer to avoid that if you could.
Well, yeah, you can do it 20,000.
I think 1,000 is kind of the level where, I mean, you start feeling it a little bit, but I think beyond that, you start really feeling it and it starts mattering. So k small is actually fairly large. It's like 1,000. Yeah?
What is meant by shared representation?
So when you are doing ImageNet with a convolutional neural network or a ResNet or whatever, you have a bunch of parameters which are used by every example going through the system. So the representation is shared in the sense that every parameter is relevant to every example, except for maybe the output layer, or where you typically have a one against all like representation. So you're learning a different predictor of, oh, it's this class versus, oh, it's not any of the other 999 classes, or any of the other 22,000 classes for the big ImageNet data set, or any of the other 100,000 classes for machine translation data sets. So when you, it's kind of a shared part, and then there's this output layer part, and that output layer part can become overwhelmingly large if you have a very large number of classes. Right? So another way to think about this is,
The shared part does not scale with the number of classes.
that's right. That's the way to think about it. So the shared part is amortized over all the classes, while the per class part is linear in the number of classes. Okay, so this is a common trick. This trick has been used effectively in many cases. Another very common trick is what we just talked about in the last 2 lectures. You have some sort of structured prediction or joint prediction problem, so you can lay out a sequence of tasks that you can then optimize towards some sort of joint performance. Right, so this is dependency parsing, but of course there are many other possibilities as well. So this is effective when you have it, but if you don't have that pre-existing structure, then you can't really do that so easily. So if we go back, this is kind of a implicit version of a hierarchy exists, right? Okay. And then the last trick is playing around with the GPU. And people have gotten very good at, or I guess the newest version of this is people have specialized hardware units to do these kinds of computations. And what's that?
This one has special.
Yeah, it's kind of it's old school at this point, isn't it? It's like 4 teraflops, I think. But you can actually do 10 teraflops with a modern GPU. And you might even be able to get more with the specialized hardware, which I think Google is playing around with. So that's kind of cool. But it's still the case that if you're doing an order 10 to the 10 computation for every photo, that's pretty painful. You wouldn't really want to do that. There's a lot of photos getting uploaded. So there's still some fundamental excessive burn of energy going on, even if you have specialized hardware, which can really pound on things. So, and it just seems like it'd be more elegant if we could come up with a solution that avoids that. Okay, so these are, I think, the common tricks, and I think often one of these tricks will work for any individual problem. But I'm not going to talk about tricks today. I'm going to talk about directly trying to learn a logarithmic time classifier. Okay, so we've gone through tricks, and now I'm going to divide this into kind of 2 pieces. In the first part, we're going to say, suppose you're given a static structure, which turns out to be a little bit more difficult than you might imagine. And the other one is going to be about actually learning a dynamic structure. You don't know in advance how you should partition things, and you want to learn. Okay, so the first thing is, how fast can we hope to go? And the answer is given by the title. So you can create multi-class classification problems very straightforwardly, where if you want to achieve 0 error rate, you have to take order log number of classes time. And how does that work? Well, we're going to create a multi-class data set where you first pick y uniformly at random, and then any prediction algorithm has to kind of use log base 2 of k bits to output the answer. And so, you have to take log base 2 of k time. So very simple. The interface itself essentially requires logarithmic time. Okay, so the thing which is interesting is this is a huge gap between what is commonly done in machine learning now and what might be possible according to this lower bound. So when you see an exponential gap, you kind of start wondering if maybe we've missed something as a field. So the question is, can we actually predict in time logarithmic of the number of classes? And the claim is that it's actually more subtle than you might have realized. So let's think about 3 classes, and let's arrange them in a tree like so. So you have 1 versus 2 or 3 at the top, and then you have 2 versus 3. And then we're going to have the probability of label 1 be 0.4, the probability of label 2 be 0.3, and the probability of label 3 be 0.3. All of these are kind of conditioned on the features, or maybe there's no features, either way. So what you would prefer is to predict the most common label, which would be class 1. That would have a 60% error rate. But if the way this works is you say, okay, at the root, I'm going to give it a label of left if it's 1 and a label of right if it's a 2 or a 3. And the probability of 2 plus the probability of 3 is going to be 0.6. And so the most common label will be right, which means you'll be locked into predicting either label 2 or label 3. Is this clear?
Yes. So why isn't it? So we split it on the so the left one is always the most probable label after this one, right? The left child.
Yeah, the left child leads to the most probable class label, but the right decision at the root has the most probability of sort of containing the correct answer rather than leading to the correct answer. So that's bad. It says that when you have a hierarchy, if you just build predictors at the nodes in the hierarchy, it says that if you have a hierarchy and there's substantial noise in your problem, if you build a predictor at the root, you may end up choosing to go a direction which kind of excludes the best answers. So that's kind of odd. It's very bad from a regret point of view because it says that your binary classifier may have 0 regret at the root, and yet you have a non-trivial regret for the overall problem. Okay. So there's a trick, and the trick is you can, instead of going from the top down, you can go from the bottom up. So if you first build a classifier for 2 versus 3, okay, so it doesn't really matter what it predicts. It'll predict either 2 or 3. And then you throw away all of the examples where that classifier makes a mistake. You'll be left with, I'll just say class 2 is the one that's chosen by that classifier. You'll be left with examples of class 2 versus the examples of class 1 at the root. And then the examples of class 1 are a 0.4 fraction, and examples of class 2 are a 0.3 fraction. So the root ends up correctly now choosing to go with class 1.
So the hierarchy is a binary tree?
It could be. I'm doing it for binary here for simplicity, but the general principle applies to multi-way hierarchies as well.
And the tree is given to us, so we can, we know what the leaves are.
Yeah.
So forth.
Yeah.
So I still don't understand why to throw away all the other examples, what difference did it make?
Yeah, so when we were learning from the top down, we were comparing the probability of 2 or 3 to the probability of 1 at the root. But if we throw away the errors and the classifier at the lower levels is correct, then we're actually comparing, instead of probability 2 or 3, you get the probability, the maximum of the probability of 2 or the probability of 3 compared to the probability of 1. Right, so we switch from an OR to a max.
Okay, this is kind of to remove the noise, right? Like the set 2 and set 3 could have noise, and we are like kind of throwing away the noise examples which our hypothesis class couldn't distinguish, right? Is that?
I mean, yes, we are throwing away examples, and yes, there is noise, and no, this problem does not exist if there is no noise in the problem trying to solve. But I guess I don't think of it as removing the noise so much as switching from this OR. So you have the probability of 2 or 3 versus the maximum of the probability of 2 or the probability of 3. And you want to compare the maximum to the maximum between 2 different subtrees in order to get the most likely label at the top.
Yeah.
Right? Because the goal is finding the most likely label, not finding the branch which has the most probability mass. So those can differ in a situation where the world is noisy.
So when you're doing this, okay, you want to classify for 2, 3. What do you mean throwing away all the error examples?
What's that?
What do you mean by throwing away all error examples?
So you have a set of examples which predict label 3, but the classifier 2 versus 3 prefers class 2.
Okay.
So you remove all the examples from your data set which predict class 3. Okay, so this approach can be composed. You can create a binary tree over your set of class labels. And when you do, you can analyze the regret bound. You can show that the multi-class regret is bounded by the average binary regret times log k. Right, and that's very intuitive because you have log k many levels to your tree, and yeah, it works out.
So what do you do if the tree is balanced?
What do you do with what?
Tree is balanced. So you have 1, 2, 3, 4.
Yeah, so I mean, the same counterexample and algorithm works when it's balanced.
But then the number of times you run the classifier, because you're going to start with all the subtrees. So you're going to do 2, 3, 1, 4, and then go up.
That's kind of a trick there.
Expecting it, because that's going to be a lot of computation.
Okay, so but it's not so much computation because you're subdividing your examples.
Mm-hmm.
So as long as your running time is linear in the number of examples,
mm-hmm.
the computation which goes on at the root is the same as computation which goes on at every other level in the tree. Right, so the tree partitions the examples,
Mm-hmm.
And that means that the computational effort going on is going to be something like number of examples times log k.
Okay.
Because an individual example, another way of saying this is that an individual example only appears in one path from the root to the leaf.
Yeah.
And so you only pay computation according to the length of that path, or the average length of that path over the examples.
Okay, but that depends. But that's if you're going from top to the bottom.
At training time, you know which leaf an example corresponds to. And so you can just work from that leaf up towards the root.
Mm-hmm. Okay.
Okay, so we might want to generalize this. Let's suppose that we have cost-sensitive classification. We talked about this previously. And so the difference is just that we have a cost for every class, right? So from typical multi-class classification. Okay, so question? Okay. Okay, so we want to train. Let's say that we're not at a leaf node, and we have a bunch of costs for every class, and we want to train to predict whether to go left or right at this internal node. So starting from the node which is closest to the leaf, we know which class the leaf corresponds to, and so we know what the costs of those two classes are. So that's the cost of A versus the cost of B. So we can compare those, and we can say, oh, well, you're supposed to go left if the cost of A is less than the cost of B, and right otherwise. So we have our class label, left or right. And then we can say the importance weight of getting this correct is equal to the difference in the costs. So we can say, you know, some importance weight, which controls how important it is to get this example correct. Okay, so that classifier will learn based upon this, and then given what the classifier learns, you will either choose to go right or left, and then depending upon whether or not it goes right or left, there'll be some class label associated with its output. Right? And that means that for other deeper nodes, including all the way up to the root, we can define a label which is conditioned on the features is associated with each edge. And that means that we can use this rule for creating a binary importance weighted classification example for all internal nodes.
Where did you get the cost from? That would be just explained.
So the costs are given in the input example. So you have an input example which has the cost for every label. And so if you have the label, you have the cost associated with that label for that example.
So the cost can be different for every example.
For every label, for every example.
Yeah.
Yes.
Normally, it's like features and correct class. So instead, we have for each class a cost, I guess. Sure.
Yeah. So you have a cost vector associated with the different class labels.
Mm-hmm. Okay.
That's a generalization. I mean, usually we'll have just ones and 1 0 there for the correct label.
If it's multiclass, yeah.
Yeah.
Yeah. So you could embed multiclass into this, and it would look like a bunch of 1s and 1 0 for the correct label. So you should be recognizing this because we use custom classification when we're talking about learning to search and joint prediction. Okay, so are there questions about how you do the training in the tree now? So your comment now does apply fully in the sense that for every node where the cost of the two labels incident on that node is different, you actually create a non-trivial example. And so the training time can blow up here.
Well, according to this, you're also doing it. I mean, you will have left. That's when you're breaking the tie here. You will still have a y. So even if the costs are equal, you will have an example here.
Oh yes, if they're equal, then you still have an example. So, but since the rule only depends upon the cost, it doesn't even matter what the label is anymore in some sense. It's for training. So here we've defined a rule where the training time in the tree. So previously, the training time for this tree was going to be logarithmic in the number of nodes, or linear in the depth. But here, it's going to be linear in the number of nodes, or exponential in the depth. So that's kind of a problem that we need to worry about. There's another issue here, which is kind of embedded in the problem itself, which is the costs, just specifying them, requires something which is order number of classes.
Mm-hmm.
So, okay, it's a drawback, but you know, what can we do? Well, this is the best generalization that we know of right now. Okay, so now you can analyze the regret. We haven't gone through much in the way of regret proofs, but and certainly will be in the papers that will attach to things. And it's not too hard to understand what's going on. So you have the regret of the binary classifier, which is induced. And then you have the cost-sensitive regret of the final output of the tree. And you want to relate these two. And you can say, oh, the regret of the cost-sensitive classifier is bounded by the average, that's what the A means here, the average regret of the 0, 1 classifiers times the expected sum of importance weights at all the nodes. Right, so we have a method here for creating importance weights, which is where we take the difference in the costs at the nodes. And it's that expected sum of importance weights at all nodes, which controls the regret ratio. So in particular, think about what this means for multi-class classification. So what is the expected sum of importance weights at all nodes going to be for multi-class classification?
What is the expectation of it? What is DFT?
So this is the distribution of binary examples created by the reduction itself. FT is the filter tree, which is named after this filtration process here. So what is the sum of importance weights going to be in a tree if you're using this kind of rule with multi-class classification? So Yoav has the correct cost vector. It's going to be 1 for every entry, except for the correct label where it's 0. Any guesses? So let's start at the root. One way is going to lead to the correct label, one way will not. So you definitely have an importance weight example at the root. Now let's go down to one level below the root. So there's the direction which did not, and now you're going to have two subtrees, each of which do not have the correct label. So the cost is each going to be 1. The difference in the costs will be 0. On the other hand, for the other subtree, which has the correct label, it'll be a 1 versus a 0. And so you're going to pay 1. And so just using that logic over and over again, how many nodes are going to have an importance weight of 1?
Half of the node.
So it's actually going to be log k.
1 for each.
So 1 for each level. Okay, so log k. It's kind of cool. But so what it says is that you actually recover this other result here. You get the log k as a corollary. Okay. Right. So it's kind of annoying that we have a regret bound which depends upon the number of classes. And this is kind of related to your initial question of, is it even possible to do this kind of thing? So is it possible to create an algorithm which would have a regret bound which is not dependent on the number of classes?
Question. So what is the like a high-level intuition behind weighting different examples differently based on importance? Like usually we do that when there is a probability distribution, like different examples are sampled with different probabilities, so we want to adjust for that.
Yeah.
But in this case, aren't all examples created equal?
Yeah.
The cost happens to be whatever it is.
Yeah. So, yeah, the importance weight is being used. It has the same semantics here as is in that kind of application, but the reason for using importance weights differs. So there you're trying to create maybe an unbiased estimate of the value of a policy, for example, right? Yeah. But here what we're trying to do is we're trying to get partial credit, right? So this is that suppose that the cost difference, so you had two examples which said go right, and the cost difference was a half. And you had one example which said go left, and the cost difference was 1. Right? So this says that in that situation, you don't really care between the two alternatives. You could go right and lose on the example with importance weight 1, or you could go left and then lose on the two examples with importance weight 1/2. So we're just trying to express the problem in a manner which is sufficiently rich to achieve a regret guarantee. Right? It gets, I mean, this becomes much more important if, I guess it's one example with an importance weight of 1 and 10 examples each with an importance weight of 1/100. So normally, if you didn't have importance weights, the 10 examples would overwhelm the one example. Yeah. But you would really prefer to go with that one example. Okay, so can you do better? Can we get rid of the logarithmic depends on the number of classes? So this is actually one that kind of bothered me for a long time.
With the same tree? With the same tree?
No, this is the correct analysis for the tree. There is no tighter analysis. You can actually prove lower bounds of a similar flavor. So what do? You have to come up with a new algorithm, right? Which you have a new analysis. So that's pretty non-trivial. But it turns out you can actually do something. So let's look at this closely. We have 8 class labels, and the black is a single elimination tournament over the 8 labels, right? So now the blue takes the losers of the black tournament and pairs them off against each other, except at the last, the last round, where both the winner and the loser go into the blue tournament. And if you count the number of entrants to the blue tournament, there's 1, 2, 3, 4, 5, 6, 7, 8 entrants, and there's 1 winner. So this is another single elimination tournament. The same thing goes with the red. And now there's something kind of cool here because so we have 3 single elimination tournaments, which are kind of embedded on top of each other. And the depth of this structure is just 1, 2, 3, 4, 5, 6, 7. So this is kind of it's hard to express this well because you really need to have a large K to do this, but the depth is really only growing a constant per single elimination tournament.
So this 1 to 8 are the classes?
Yeah.
And but in the description on the left it says examples are competing, right?
The example means the class. Yeah, so once an example predicts incorrectly, is predicted incorrectly, it moves to the next tournament over. Right. So in the filter tree, what would happen is if an example lost, it would be discarded at this node here. But in a error correcting tournament, it's not discarded. Instead, it just moves to the blue tournament. Okay, so this is kind of cool. The depth here is essentially going to be order log number of classes, as long as we only have log many tournaments. And then once you've reduced things to log many winners, you can do something much more careful in terms of comparing things. So you can have you can afford to have much larger importance weights. So what that corresponds to is kind of, I think in the NBA, they have these tournaments where teams have to play each other. And the number of times they have to play each other in order to get a majority win increases as they go towards the root. It's that kind of structure which is implied here. Is the question?
What's that in reference to? Sorry.
So in basketball tournaments.
Yeah, I know how that works, but I'm just, what's that example in reference to?
I'm explaining how this last tournament is handled. So the structure where you have these overlapping single elimination tournaments produces log K many winners.
Right.
And then those winners may not be the same.
Right.
So you need to actually, I mean, if you're lucky, they're all the same and it's all trivial. But if you're not lucky, then they may be all different. And now you need to choose amongst log K possibilities to see who's the winner.
Right.
And now you can afford to do something much more expensive on those log K possibilities.
I see.
Yeah,
Okay.
like the NBA playoffs.
Yeah.
Okay, so what can you prove? So if you have a multi-class classification problem, you can do an error correcting tournament. You can prove that if less than 1 in 5.5 of your classifiers is wrong, you'll get the right answer at the end. With constant classification, you get, okay, so the results are less impressive because the training time is linear in the number of classes. The test time remains logarithmic, and the constancy of regret is not as impressive in general for constant classification. Okay, so are there questions about this?
Is there a reason why you put O's on the orientation of the other correcting tool?
Yeah, and the constant is no longer 1, right? So the multi-class computation is now going to be something like 2 or 3 log K for an error correcting tournament.
Mm-hmm.
So let me go here. So I have a data set, which is a 1,000 class classification data set. So by the standards of the kind of problems we're trying to deal with, this is kind of a toy problem. But nevertheless, we can try to train on it. So this is doing an error correcting tournament. It's actually a filter tree by default. I'm training with 10 passes on a data set. It's very fast, and I end up getting an average loss of 80%. So it's non-trivial because 1 in 1,000 would be 99.9% error rate. But this is still not terribly impressive because it's an 80% error rate. Okay, so let's talk about contextual advantage for a moment. Actually, let's not. So I'll leave this for later. There's a trick very similar to the filter tree for doing this with contextual bandits. I want to spend time talking about actually learning the structure. So let's skip this for the moment. Blah, 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 blah. Okay. So dynamic structure. We want to, okay, so why do we have an 80% error rate here? Why isn't it much, much smaller? So if we go and we look at 1 against all here, it's not terribly fast. It is slower, but the error rates that we're getting are much, much better, right? So this is progressive validation in the last 30,000 examples is down to 31% error rate, right? And then we have a holdout loss, which is at 35%, and it's going to keep falling. So there's a big gap between 35% and 80%. It matters why we lose so much. And the question is, why do we lose so much?
In the previous example, like what structure did we use? Like, was it like something?
Yeah, so it was using the binary representation of a label.
So there's no actual information in
It was arbitrary.
Yeah, that's right. Yeah, so we're using an arbitrary structure, and that may not be very well aligned with what a classifier can predict well on. Okay, so imagine that you're trying to create a digit classifier. So think about MNIST, and you can either do a tree which has a subtree of 1 versus 7 and a subtree of 3 versus 8, or you can do a tree with a subtree of 1 versus 8 and a subtree of 3 versus 7. Right, so which is actually going to be better?
The 1 and 7 versus 2.
Why?
Because like the first split will be easier because distinguishing 1 and 7 versus 3 and 2 will be easier.
But the second split will be harder, right? Because splitting 1 versus 7 is harder than splitting 3 versus 7.
But like once we make an error at the top, we cannot recover. Like we cannot improve. Right?
So your intuition is correct, but it's just slightly more subtle. The problem is that the root has all the examples instant on it, and that means that it tends to be very over-constrained. So there's a lot. It's forced to make errors because it just can't even represent the solution effectively. And that means that you want to deconflict the root as much as you can. Right, so that was the basic observation in this paper. It's better to have confusing decisions near the leaves than near the root. Okay, so
information gain.
Yeah, so you want to think about information gain criteria. We'll get there in a minute.
Near the leaves, you can't confuse by among that many classes because you already dropped those.
What's that?
Near the leaves, you already subtracted everything is not in your subtree.
Yeah.
So the confusion potential is much smaller to start with.
There's certainly a lot less, much fewer constraints that you would like a leaf words classifier to obey. So 1 and 7 may still look very similar, even if they're near the leaves. So I mean, it may be a little bit subtle to. I can't always distinguish my child's 1 versus 7, but all you have to worry about is 1 versus 7. You don't have to also worry about 3 versus 8. That makes it a lot easier. Okay, so I guess a claim is that if we're going to try to dynamically learn structure, the problem that we're trying to solve is not classification. It's fundamentally different from classification. It's actually partition. And so what do I mean by that? What I mean is that, okay, so if you're trying to solve partition, you could take a classifier that predicts, left or right, and you could negate it. So it predicts right or left. And that would be just as valuable, right? But in classification, this would be terrible. You go from 0% error rate to 100% error rate. So the nature of the problem is fundamentally different because of that. Okay, so this is one way to talk about what a good partition is here. You have some distribution over examples, x, y. You have the probability that you predict right, which is h of x equals 1, and then times the probability of y, and then you have the probability of jointly predicting right and the y. So this is kind of like a notion of dependence, right? So if this value is 0, then you're kind of predicting independently of the class label. If this value is large, then the class label is strongly correlated with the right or left prediction. Okay, so you can factor out the probability of y, and then you can see that you're kind of comparing the marginal probability of going right to the probability of going right conditioned on the class label. And then this is all weighted according to the proportion of the labels in the data set itself. Okay, so this is a criteria. You would like to maximize this criteria in order to achieve a good partition. Okay, so this is horribly difficult in general, because if your hypothesis class is symmetric, then you lose. So what I mean by that is, if for every hypothesis class, if for every hypothesis doing a left versus right split, there's another hypothesis which does the opposite. It's a symmetric class. And the convex combination of those two classifiers will end up essentially predicting large, right? There'll be some in-between point where there's a switchover, and what happens there is undefined. So this is certainly not convex. It's not a convex criterion. Now, there's been a lot of people who play around with machine learning with non-convex classes, and they've been very successful. So we shouldn't be too afraid of that necessarily. But it says that we're not going to be able to get the same kinds of guarantees you might hope to get with a convex problem. Okay, so so let me tell you some more bad news. So we argued before that we needed to worry about kind of training from the bottom up in order to minimize the regret. Okay, so that doesn't work. And the way to see this is, suppose you have a feature which is just the position on the x-axis here. So you have 1, 2, and 3. So 1, 2, and 3 are the class labels. The feature that corresponds to them is, x equals 1, x equals 2, or x equals 3. So this is very simple. So if you wanted to do something in a bottom-up fashion, you wouldn't know any structure in advance. You have to pair things, and you have to try to predict between the two. So suppose you pair 1 and 3. So you can build a good 1 versus 3 predictor. That's relatively straightforward. And then you need to pair a 2 versus the winner of 1 versus 3. And then you're going to fail because there is no threshold on the line. Well, you'll fail with linear predictors because there's no threshold on your one feature which can actually distinguish between these two. So training in a bottom-up fashion for a dynamically learned structure seems to be difficult. Okay, so now the question is, how do you actually train to partition? So I'm going to go through an approach to doing this. And the critical thing is, how do you actually train an individual node? And then, we're going to have a tree, and then we're going to apply the same rule at all the different nodes, and then something will happen, right? But the critical bit of the algorithm is, how do you actually do the training at an individual node? So we have some individual node, we have some example. It's a multi-class example. So the first thing we're going to do is we're going to compute the Shannon entropy. Does everybody know Shannon entropy? Yeah? Okay, so you have the left subtree and you have the right subtree. You have the distribution of labels incident on the left subtree, the distribution of labels incident on the right subtree. So for each of these, you can compute the Shannon entropy, and you can also compute the Shannon entropy with y added into that empirical distribution. All right, so the h hat left is the empirical Shannon entropy of the left subtree, and the h prime hat left is the Shannon entropy of the left subtree with that new label added in. All right, and similarly for the right. So then you can compute kind of, so what you're trying to figure out is a label. You want to know if you should go left or right. So what we're going to do is we're going to try to minimize the Shannon entropy as we descend down the tree, because minimizing the Shannon entropy is progress towards getting a good classifier. So given that you go left, you use the h hat prime left and plus the h hat right, and vice versa if you go right. And so this is kind of what will my entropy be after I take a step to either the left or to the right in expectation for that level. Okay, so who here has seen sort of decision tree learning in the past? Okay, so you're familiar with like optimizing Shannon entropy as you go down the decision tree. The difference here is that we're going to actually try to do this by reduction. So instead of testing Shannon entropy against a threshold and an attribute, we're going to create a binary importance weighted classification example. Okay, so the difference in the left versus the right, average Shannon entropies is this delta H hat, and then we can create an importance weighted binary data example where, oops, okay, so the label is the sign of that difference in entropies, and then the importance weight is equal to the magnitude. Okay, so this is a way to take the partition problem, which we've defined here, and optimize Shannon entropy to try to work with the partition problem using a reduction to binary classification, or importance weighted binary classification. Okay, so this is some important tricks that you want to do on top of this. We've defined how we're going to train at a node. Descending a tree is a straightforward thing, but you don't actually want to go all the way to a leaf because the number of examples at a leaf becomes too small. So you want to halt early. And now when you halt early, there's going to be a set of possible labels. So you need to figure out which one to predict. So what we're going to do is we're going to train a separate set of one against some classifier. So when you're training one against all, you train that one class against an imposter set, which is all possibilities other than that class. When you train one against some, you're training that one class versus the other labels in a leaf. Right, so that as long as the number of labels in a leaf is logarithmic in k, this is still a logarithmic time algorithm. Controlling when you halt is a little bit tricky because the empirical entropies and empirical recalls of a tree are misleading statistically. So you need to have a bound. And then you want to actually, it's useful to add in a feature as you descend, which is the node that you descend through. And the reason why it's useful is because it allows the one against some predictor to actually do better than a one against all predictor could do. Because it can represent things that a tree can represent naturally, but which the one against some structure or one against all structure could not. I didn't explain that well. So trees are very good at doing hard splits, left versus right. A one against all representation is instead like a Voronoi diagram. Because, okay, so let's suppose that all of your weight vectors have the same magnitude. Then what you would be asking for any individual example is, which of these prototype vectors am I closest to? It would be exactly a Voronoi diagram. Now the weights are not all the same in a one against all representation, or the same magnitude. So really what happens is you're essentially solving a weighted Voronoi diagram problem, right? So some of the cells in the Voronoi diagram are kind of given more weight than others. And that's what the Voronoi diagram is doing in a high-dimensional space. So a Voronoi diagram can't do a strong, there's some things that it cannot represent very well. So if you have three classes, you're going to have some sort of intersection point between those three classes. On the other hand, a tree could actually just do a split like this, which can't be represented by the Voronoi diagram. So there'll just be a straight line. There's no way to change the importance weights on a weighted Voronoi diagram to achieve the same kind of structure. So if the truth is similar to a tree, then you would like to be able to represent this. And one way to make that representable is to add in the actual node IDs as features. Okay. All right, so you can prove a boosting theorem. So I think this is kind of important because we're training at a bunch of different nodes, and it'd be nice to know that everything kind of orchestrates together to achieve a small error rate. So what is the boosting theorem? So we have the entropy. We need to have a weak learning assumption. The weak learning assumption is that we have some entropy incident on a node, that's Hn. We have the entropy of the left and right subchilds, weighted according to the fraction of examples going to left versus right. And we would like that the average entropy of the children is less by some gamma than the entropy of the node. So it seems like the natural notion of a weak learning for, at least a natural notion of weak learning for partitioning. Okay, so then you can prove a theorem. It says that if you achieve gamma weak learning at the different nodes, then after T splits, the error rate is going to be reduced to something like the initial entropy minus gamma log T. And that kind of makes sense because log T is the depth of the tree. So it's like every level in the tree is giving you a gamma size improvement on things. Okay, so we did some tests with this. There's some algorithms here. Okay, well let's just go here. So I did one against all here, and you can see that it actually gave reasonably good performance. Got down to 15% error rate on a holdout. I can also do dash. I think it's recall tree. So this will run, and we'll find that it gets down to about 18% error rate. So 18% is much better than 80% error rate. And if you tune things a little bit, you can actually get it to work better than one against all. So there's three things being compared in this figure. One of them is a one against all. One of them is the recall tree, which is in gray. And a third one is the LOM tree, which is an earlier algorithm that I worked on with Anna Kwarmanska. So if you look at the performance here, you see that the recall tree is sometimes better than one against all, statistically. Sometimes worse, I would say more typically worse. It tends to be better than the LOM tree. So let me, yes, okay, so we got down to 18% here. If we want to do LOM tree, we can do it like this. And we'll see that the performance that you get is actually pretty terrible, unless you do a trick. So the LOM tree was an earlier approach, and okay, so it got pretty terrible performance. So you can actually kind of over provision the tree. You can say, oh, I allow you to have 8,000 nodes rather than 1,000 nodes, and then its performance will improve somewhat. So, but okay, so what am I trying to say here? I'm trying to say that for these larger data sets, where the state of your predictor starts to matter a lot, it's important that your algorithm doesn't use excessive state. And the LOM tree does use excessive state for the ODP results and the ImageNet results here. This is, by the way, on the ImageNet 22K data set. It's the big one, not the smaller one. All right, so a LOM tree with a whole bunch of extra nodes gets down to 22% error rate. Okay, so are there questions about this? So another thing which is kind of enabled by these algorithms is you can actually do an online logarithmic time learning. So you can run through, so we found another data set, LTCB, where there was actually some ordering to things. You can run through, and you can see that if you run through in order, your performance is actually better than if you run through on a permuted version of the data set. So that's nice. So in addition, I guess, to getting logarithmic multi-time, we're doing online logarithmic multi-time. I think it's important if we want to think about trying to apply these algorithms in settings where you're doing online optimization. Oh, and this is the path features. So you can turn off or turn on the path features, and you can see that the performance is substantially better with path features. Okay, so can we predict in time logarithmic in number of classes? And I don't think the answer is fully, I don't think that's fully answered yet, because it's still the case that there's some gap in performance. So the 0 here is the performance of 1 against all, right? So for these larger data sets, it's still the case that there's some gap between what we can achieve with 1 against all representation, which is the standard, and what we can achieve with a logarithmic time representation. I haven't shown you the computational times graphs, but it is really the case that you do predict in logarithmic time with these algorithms. So I think ODP is about 100,000 classes, and it makes a big difference what you use. So I don't think it's entirely answered, but there are sort of more directions for improvement possible. It would be nice to figure out how to get consistency, like in the first part of the lecture, with a dynamic partition, like in the second part of the lecture. There's also, it's kind of, so there's a bunch of tricks here for trying to not have too few examples going onto a node, well, and get good prediction performance. Because when you have too few examples going to a node, it can be rather sloppy what gets learned. the node becomes very under-constrained, and then it becomes difficult to learn in a manner which is not overfit. So I don't think that's handled perfectly here. There's other issues like you would like to, so here we have state, which is linear in the number of classes. It'd be nice to have state, which is logarithmic of the number of classes. There's actually a trick, which I haven't really covered, which may lead us there. It involves dynamic programming, which is sometimes magical. Okay, so there's a bibliography. Are there questions?
I have a question about like so there are multi-label classification problems, right? So is it good that we just solve them using such methods and like use the probability as like let's say we want to give an rank or we want to give top 10 labels. So like is this the right direction to go or are there other?
So this is not a complete answer about how to handle multi-label, because here we're kind of optimizing the situation where you should go right or left. There's hard decisions involved. But in multi-label settings, maybe there are 3 right answers out of 100,000, right? And then it's a little bit less clear. I mean, maybe you have a right answer to the left and a right answer to the right. And what you should do is not really addressed. So I think that there are variants of this which could be used for multi-label, but we haven't really spent a lot of time on that. There is there's a line of work coming from Manik Varma in India, which is trying to directly address multi-label efficiently. He's not worrying about logarithmic time necessarily, but he's worrying about efficient algorithms, so sublinear time, and that looks fairly effective.
What's the name of the researcher?
Manik Varma, V-A-R-M-A. I'll add a link to when I put this up on the webpage.
So even in these methods, do we assign probabilities to each class? Like can we have this to give? No, right?
No. No, this is just designed to answer the question of what is the label. And assigning probabilities to each class requires, I mean, actually doing that would require order k time. Now there's another paper I didn't just cover here, another approach I didn't cover, which involves, instead of classifying at the nodes, let's go here. Instead of classifying at the nodes, let's even go back further, right? Instead of classifying at the nodes, you could predict the conditional probability of going left or right. And then you can multiply together the probabilities as you go down the tree in order to extract probability for the leaf. Right. So there's work along these lines. There's something from Yashua and there's something that we worked on earlier. That's probably worth revisiting because we've learned a lot about how to do things dynamically since then. So that would be a way to implicitly assign a distribution over labels, because the probability of the label is, for any individual label, is the multiplication of the probabilities as you go down the tree.
So, but in that case, we can still do it in like logarithmic time, right? Like we don't need to, because I was thinking maybe you're saying that we require linear time because we need to normalize or something.
So you can specify the probability of any individual label in logarithmic time. If you want to extract the label with the largest probability, that would not be logarithmic time anymore necessarily. Because you have to do some sort of like alpha beta pruning or something going down the tree, which would maybe in general be like order root k. It might even be worse. It might be order k. So if all the labels have very similar probabilities, then figuring out which one has the largest probability could be essentially an order K search, because maybe you have to kind of instantiate every leaf words node to figure out what the most probable class is. Right, so that would be bad. Now, maybe that doesn't happen in practice. Maybe it's the case that only a few of the paths have a substantial probability mass. That's what you would hope for. And then the time required to find the most probable path is going to be related to the number of paths which have a non-significant probability. Okay, thank you.
Thank you.